and we'll see how it goes. Okay, so we're going to spend today and then Tuesday of next week looking in at trying to dive a little bit deeper into some of uh, the classes of enzymes and looking at some of the common themes in the chemistry that these enzymes catalyze. And the first one we're going to look at is oxidoreductases. Um, in metabolism, oxidoreductases are really common and really important, especially when you start thinking about the chemistry that happens in glycolysis, the TCA cycle, and the mitochondrial electron transport chain, right? So these pathways that are ultimately responsible for producing energy for us. Electrochemistry is incredibly important, and why does this keep advancing automatically? Electrochemistry is really, really important. Um, at the end of the day, metabolism to a large degree boils down to redox chemistry. We are starting off with carbon in the form of a sugar in a fairly reduced form. And through the process of glycolysis in the TCA cycle, we are oxidizing it all the way down to carbon dioxide. So we are oxidizing it as far as possible, pulling electrons out of it, right? And those electrons then go into the mitochondrial electron transport chain to produce energy. Okay, and we're going to look at that in a lot of detail later in the semester. But for now, let's focus in on what we mean by oxidoreductases, right? So they catalyze electrochemical reactions. And hopefully you remember that electrochemical reactions boil down to reactions that transfer electrons from one atom or more than one atoms to another, okay? They all have an oxidation component and a reduction component, and we call these half reactions. So the oxidation half reaction is the reaction that produces electrons, and the reduction half reaction is the one that consumes electrons. Okay, and there are lots of ways to remember which way it goes and what's what. Oil, like lots of acronyms like oil rig and Leo says GER, losing electrons is oxidation, gaining electrons is reduction. For me, what works the best is to just look at the reaction, and if the electrons are reactants, it's a reduction. So write out the reaction, which ultimately you need to do anyway for these redox reactions. Write out the half reaction, and if the electrons are present as a reactant, it's a reduction. That's a reaction that's consuming electrons. The opposite is true for oxidation. If the electrons are produced, it's an oxidation. So for me, the easiest thing to remember is electrons as reactants is the reduction, but whatever works for you. Each of these half reactions is characterized by something called its redox potential. And we usually represent them in terms of reduction potentials. And that's an important thing to remember moving forward today, is that typically the potential value, this E naught, is almost always represented as a reduction potential. Okay, when we tabulate them, they are reduction reactions. And ultimately, these potentials are related to the Gibbs free energy, right? To the spontaneity of a reaction. Okay. The really important thing to note here is the relationship between the signs. We know that for a spontaneous reaction, a negative delta G is good, right? If we want the reaction to be energetically favorable, we need delta G to be negative. And since there's a negative sign in this equation, this is called the Nernst equation, since there's a negative sign here, that means that we want our potential to be positive. So a positive potential corresponds to an energetically favorable redox reaction. Okay, that's an important thing to remember. So when we look up these potential values, if we see a positive value, that means it's energetically favorable. It will be characterized by a spontaneous Gibbs free energy. If we have a negative potential, then it's going to be a non-spontaneous Gibbs free energy. It's a really important thing to keep in mind as we move forward. Okay, other important terms is reducing agent or reductant and oxidizing agent or oxidant. Okay, and these are kind of flipped in terms of an oxidation reaction and a reduction reaction. A reductant or a strong reducing agent is one that drives the reduction reaction. So it's something that allows a reduction reaction to happen. So the reducing agent is actually the molecule that gets oxidized. So in an electrochemical reaction, the reducing agent gets oxidized because it allows the reducing reaction to happen. Reducing agents get oxidized, oxidizing agents get reduced. So a good reducing agent is one that readily donates electrons so that something else can get reduced. Okay? A good reducing agent is a molecule that will readily be oxidized, and that will be characterized by a very negative reduction potential. Okay? Because these potentials are always listed as reduction potentials, something that's good at getting oxidized will not be good at getting reduced. So it will have a negative, non-spontaneous reduction potential. The opposite is true for a good oxidizing agent. Something that is readily oxidized, something that's readily reduced, or a good oxidizing agent, will have a spontaneous, very favorable reduction potential. So we would expect that to be a positive value because of positive potential means a negative delta G. Okay, so the names, if you think about them, make sense, but they're kind of opposite in terms of the words oxidation and reduction. The reductant or reducing agent gets oxidized. The oxidant or oxidizing agent gets reduced. Okay, and these values, always represented in terms of the reduction direction, they are related to the Gibbs free energy. Okay, and in this equation, N is the number of electrons transferred in the overall electrochemical reaction, and F is Faraday's constant, which you can look up. It's 96,485 joules per volt mole. Okay? Hopefully that's all things that you kind of remember. I mentioned that these potential values are always tabulated, right? So we can readily look them up and find them. And you're always going to find some sort of a table of standard reduction potentials. And I'll note here, they are reduction potentials. So, God damn it. I don't know why it keeps doing this. So all of these reactions are listed in the reducing direction, okay? So the idea here is in the first column, this would be our reactants. And since this is a reduction reaction, electrons will also be reductants. So in this first case, succinate and carbon dioxide would be reactants along with electrons. The product would be this molecule alpha ketoglutarate. This is a weird one because it's probably something most of y'all haven't heard of, and you will by the end of the semester. But we can think about easier things, right? So something like iron 3 becoming iron 2. It's a very straightforward electrochemical reaction. Iron deficient of 3 electrons becomes iron deficient of 2 electrons. So it's really easy to envision this needing to pick up 1 electron to become this. And that's the case for everything here. The reactants gain at least 1 electron, and the number of electrons is listed here, gains at least 1 electron, and it becomes your products. Okay, so in this case, what's listed as the reactant is the molecule that gets reduced. So that's the oxidant or oxidizing agent. And the molecule listed as the product is our reductant. That's, if this were the reactant, we would call this the reductant. So if we were to reverse the reaction and this became your reactant, it would be the reductant, the molecule that gets oxidized. Okay, so these reactions as listed are the reducing reactions, and they're characterized by a specific potential. You're going to need to think about reversing these reactions to see the oxidizing direction, right? So iron 2 becoming iron 3 and producing an electron. When you do that, just like any other thermodynamic function, the sign changes, right? So in the reducing direction, iron 3 becoming iron 2 has a potential of 0.77 volts. Reverse it, that potential is negative 0.77 volts. Nothing especially surprising. Okay, so let's think about an example here, something really simple, and let's also see if this automatically advances so I can curse again. All right, so let's see if a very, very simple example here. We have this overall reaction where X is becoming X plus, right? So it's giving away an electron, so X is being oxidized. I gotta figure out what the hell's happening with this. And Y is becoming an anion, so it's gaining an electron, so it's being reduced. So we break this overall reaction down into the half reactions. We identify the oxidation half reaction and the reduction half reaction, and then you look these up in a table, right? So you'll always find them in the reduction direction. So this reaction will be found directly in a table. It has a potential of 1 volt. You will not find the oxidation reaction in the table, but you'll find the reverse of it. So you would find X plus plus E minus becoming X. And in the table, that would have a value of negative 0.5. And since you reversed it, it becomes positive 0.5. So the idea here is simple. It's Hess's law, right? Hopefully you remember a little bit of something about Hess's law. So the idea with Hess's law is that when you add up two reactions, right, when these two sides add up, our electrons cancel out. We end up with X plus Y becoming X plus Y minus, right? So our products end up on our product side. Our reactants end up on our reactant side. When we add up the two reactions, we also add up our potentials. So in this case, the overall potential for this reaction is 1.5 volts. So the overall potential for this redox reaction is a positive number. And that's relevant because a positive potential corresponds to a negative delta G, right? According to our equation, when our potential is positive, our delta G is negative. So this is a spontaneous reaction as written. If we were to reverse it, the process would be the same. You'd go through the same process, but in this case, this would end up being negative 0.5. This would be negative 1. The overall potential would be negative 1.5. So it would be non-spontaneous in the opposite direction. And if you needed to calculate the actual value for delta G, N is 1 here. We cancel out 1 electron. F is Faraday's constant. It's a value of 96485. Just plug it in, and then it's 1.5 volts. So it's a very straightforward calculation. The trick is just to remember that you need your potential in volts, and N is the number of electrons that you cancel out, and they have to cancel, right? When you combine your oxidation and reduction reaction, the number of electrons must cancel out. Okay, so hopefully all of this is at least somewhat review. But the one thing that I want to point out that maybe has never been pointed out to you is that we can identify themes in these potentials, okay? So when you're looking here, let's use this reaction as an example, okay? H2, it's becoming FAD. This is an oxidation reaction. We are taking NAD plus and it's becoming NADH. That's the reduction reaction, okay? And we can break these down into our half reactions. Somebody tell me what's happening. We can break these down into our half reactions, and we can find these half reactions in our table, okay? The reduction reaction we find directly. So the reduction reaction we see right here. NAD plus, gaining 2 electrons, becoming NADH and H plus. Yeah, I put the H in the wrong place, but y'all get the idea, right? So here, this value of negative 0.32 comes right from the table, right? We see it right here, negative 0.32. Our oxidation reaction of FADH2, we don't see direct, right? So here, FADH2, the reverse is FADH2 becomes FAD. This value of negative 0.22 we have to reverse. So the value of the potential we get here is plus 0.22. Okay, so hopefully that's straightforward. When we add these together, what we notice here is that we end up with a negative overall potential, negative 0.1 volts. So as written, this reaction is not favorable. Okay, if we were to reverse it, the reaction would be favorable. And the theme that I want you to pick up on and identify and really kind of zone in on is that whenever your oxidation reaction in this table appears below the reduction reaction, it is a non-spontaneous reaction. When the potential for your oxidation reaction is less positive than your reduction reaction, then it's going to be non-spontaneous. Okay, so the positioning of the oxidation reaction relative to the reduction reaction matters. In this case, our reduction reaction is above the oxidation reaction. So according to this table, this is a non-spontaneous process. If we reverse it, all of a sudden the reduction is below the oxidation and that becomes spontaneous. So the relative position in the table will always tell you if the reaction is spontaneous or not. In this table, if your oxidation reaction, right, so our oxidation reaction is below the reduction reaction, it will be non-spontaneous. If the oxidation reaction is above the reduction reaction, it will be spontaneous. And for the most part, that's what we care about. Look at a table, quickly say, is it spontaneous or not? That's it. If you needed to calculate delta G, you could, but usually we don't really need to. All right, so with that, we'll go ahead and work